All right, let's get started with Lesson 8, VESPR theory. Now that you understand Lewis dot structures and how to write and represent them, now we can get into talking about the geometric shapes of molecules. Now, molecules are not flat. They're not just these flat surface things. They are actually three-dimensional. Because they're three-dimensional, they have geometric shape or geometry. And we're going to learn about how to name these shapes today, the angles between the bonds, and how we would actually eventually be able to make models or model representations of these geometric shapes for these molecules. Now, the VESPR theory is the theory that helps us to predict the geometry of these molecules. So what exactly is the VESPR theory? What does it mean? V stands for valence, S stands for shell, E stands for electron, P stands for pair, and R stands for repulsion. So put it all together, we have valence, shell, electron, pair, repulsion. Now the name VESPR applies to us that it gives us kind of the indication of how the VESPR theory works. We're talking about valence electrons, so they're in the valence electron shell, and the pairs of electrons repel each other. And I think you already understand that electrons in the valence shell do repel each other. They want to get as far away from each other as possible, and that idea is going to predict the geometry of these molecules. All right, so as we go through this lecture video or lesson, make sure you remember, keep that in mind, that the valence electrons want to be as far away from each other as possible, and that is going to determine the shape of these molecules. All right, so the key three. These are the three key points that I need you to understand about the VESPR theory in order to predict the geometry of these molecules. So I'm going to highlight a few things as we go through them. So number one, you're going to count the number of electron pairs or electron domains, okay, around the central atom. So electron domains include all the bonding pairs and the lone pairs around the central atom. You're going to treat, and this is really important, you're going to treat double and triple bonds as if they were single bonds in this case. And that is just because each triple and double bond and single bond counts as one electron domain each. All right, so we'll point out electron domains as we look at these geometric structures here in a minute. Okay, number two, as we mentioned earlier, electron pairs repel each other, and that repelling then is going to create a position where the electron domains are far away from each other as possible. So that's the key idea. One is you got to know how many electron domains there are, and then you got to position the electron domains as far away from each other as possible in order to predict the overall geometry. All right. Now this last point, very important to keep in mind, is that the lone pairs are going to repel another lone pair a lot more strongly than bonding pairs will. What I mean by this, and you can make note of this, is that the bonding pairs, the lone pairs, so make a note of this in your notes, lone pairs need more room, more space than the bonding pairs do. And because the lone pairs need more space, it's going to have a direct impact on the molecular geometry or shape of these molecules. All right, so let's start out with our first geometric shape. All right, it's a linear structure. Now, in this linear structure, we're going to have two electron domains. We have an electron domain here. Oops, let me use a pen instead. So we have an electron domain there and an electron domain there around the central atoms. So we have 2 electron domains around the central atom. Now, because we have 2 electron domains, what is the furthest apart that you can get these 2 electron domains? It would be 180 degrees. So the angle here is a 180 degree angle between those 2 electron domains. And therefore, a 180 degree angle is going to give us a linear structure. A good example of this is carbon dioxide, CO2. If you draw the Lewis dot structure of CO2, you would find that it would look something like this. All right. It has how many electron domains? 2. Remember, each double bond counts as 1 electron domain. So we have an electron domain there and an electron domain there. Now, we only consider electron domains, again, around the central atom. So we don't care about the lone pairs on the oxygens because they're not central. And the geometry, the whole geometry, is determined about basically the domains around the central atom, right? So carbon dioxide has 2 electron domains around the central atom. Therefore, it has an angle of 180 degrees, and therefore it results in a linear shape, all right? So when you do Lewis dot structures from now on, this is one of the things I'm going to ask you to do, is once the structure is written down or drawn out, you're going to then predict what the geometry is. All right, so let's go to the next deal. All right, if you look here at these 2, they have 3 electron domains. All right, you have an electron domain there, there, and there. Okay. The other structure, you also have 3 electron domains. 1, 2, and that lone pair is also considered an electron domain around the central atom. So these all have 3 electron domains. Okay. So the question is, if you have 3 electron domains around a central atom and you want to space them out so they get as far away from each other as possible, what is the largest angle you can make? Well, it turns out, you can probably guess it, but it turns out that the largest angle is 120 degrees. All right, so each one of those electron domains is 120 degrees away from each other. So an example for this is like, let's do COH, okay? We have some lone pairs on that oxygen, okay? And this is a great example. And by the way, this would be known as a trigonal planar structure, trigonal planar. And if you look at it, it has a triangular structure. In fact, I'll erase this and I'll come back to this when we show you the triangle structure here. So if you look at this, it has a triangle from domain to domain. There's your triangle, and it's flat, which gives you your trigonal planar because it's a flat surface. All right, and that's why they call it a trigonal planar. Okay, so again, 120 degree angles. And then we're going to go back, we'll write in our structure here. Right. Lone pairs on that oxygen. Now, again, the lone pairs on the oxygen don't matter because our central atom is carbon. So therefore it has 1 electron domain, 2 electron domains, and then a 3rd electron domain. All right. So there are 3 electron domains around the central atom. Therefore, this must be trigonal planar, and the angle is 120 degrees. All right, so that's trigonal planar. Now, the next one that has 3 electron domains, something different about it, it has a lone pair of electrons. Now, that lone pair of electrons is going to make a significant contribution to the bond angle that exists for this, what we call a bent molecule. remember that lone pairs need more space. Because those lone pairs need more space, they're literally going to push down and repel these bonding pairs with a greater force of repulsion. So these two domains that are bonding pair domains are going to actually be squished together a little bit more. So they're going to have to squeeze a little bit tighter together. So that's going to reduce the bond angle between those bonding electron domains, and that's going to make an angle of 117 degrees instead of 120, all because those lone pairs need more room or more space. All right, a good example of a molecule that has a bent shape with one lone pair would be example of SO2. So SO2 here, and it's going to have a lone pair on the sulfur and double bonds with both of those oxygens. Actually, no, not a double bond. I'm sorry. Those are going to be single bonds. And then the oxygen will have dots around it for lone pairs. But again, we don't worry about those because they're not central atoms. So only the sulfur has 3 electron domains. 1 electron domain for those lone pairs, electron domain for the bonds, giving us 3. So that gives us a bond angle of 117 degrees, and we have a bent shape. And remember that lone pair is pushing with a greater force or needs more space than the bonding pairs, so they squeeze together. Okay? So there's a bent shape. Okay, our next series actually contains 4 electron domains. So if you look closely, all of these 1, 2, 3, 4, 1, 2, 3, 4 with that lone pair, and 1, 2, 3, 4 with those lone pairs. Okay, so all of these have 4 electron domains. So write that up here, 4 electron domains. Okay, all of these. So let's look at the tetrahedral structure first. A tetrahedral structure has 4 electron domains and 3-dimensional arrangement. What is the furthest angles that we can make with those 4 electron domains? It turns out to be about 109.5 degrees. Okay, 109.5 degrees angles for those electron domains. A good example would be methane, CH4, which has a Lewis structure like so, with those 4 electron domains and 109.5 degrees. Okay. All right. So there's tetrahedral. A trigonal pyramidal now, a little different. It still has the 4 electron domains, but now has a lone pair of electrons, as you can see here. So what's going to happen with those bond angles with a lone pair of electrons? Well, the lone pair again needs more space, and so it's going to squish or squeeze these 3 bonding pairs closer together, and so the angle is going to be smaller than 109.5. So what do you think the angle might be? Well, it's going to end up being 107 degrees. Okay, just a little bit smaller than the 109.5 due to that lone pair. Okay, so what's a good example? I think ammonia is a great example. Ammonia has a Lewis dot structure that looks like this, with a lone pair on it, right? And therefore, that lone pair is going to squeeze these bonding pairs together to make an angle of 107 degrees. All right. So there's a trigonal pyramidal. All right. Let's go to the next one, bent shape. Here's a second bent shape. The difference here, though, is that it has 4 electron domains, and the other bent shape only had 3 electron domains. This one has 4. It has 2 bonding pairs and it has 2 lone pairs that makes those 4 electron domains. Now, because we have even more lone pairs of electrons, that's going to cause these bonding pairs to even become squeezed even closer together, so that bond angle right here should get smaller. And so what do you think? What do you think your prediction is? Well, if you predicted it was going to be 105 degrees, you would be correct. So the bond angle in that bench shape is 105 degrees. A great example would be, I think, water. Water definitely has this bench shape to it. Something you should always know. Water has a bench shape. Has 2 lone pairs in its structure. Therefore, this angle is 105 degrees, making it much smaller. All right? All right. So these structures that we have currently gone through, all the way from linear to now this second bench shape, these are the basic structures that we find in nature. All these geometrical shapes are very, very common. And so most of the time, these are the structures that we're going to come across. However, the next set of structures are very rare and unique. And there's a problem with these structures. And that is, these structures do not obey the octet rule. Again, I will repeat. These next series of structures do not obey the octet rule. They violate it by allowing more electrons to be around the valence shell, essentially. Okay, so what do we call this? Well, let's write this down. Somewhere write this down. Let's do this. These are going to create what we call expanded. Oops. I'm going to run out of room. Let me write it. Just write it somewhere. I'm just going to write it here in big so you can kind of see it. So expanded valence shells. Okay? And what expanded valence shells are, it's just that the central atom, and we're talking only the central atom here, has the ability to have more than 8 valence electrons around it. So it makes for a little bit more challenging situation. Okay. Now, honestly, most of these structures do not exist naturally in nature. A lot of them are made by man in laboratories, okay? But you do need to know these structures, and you need to know the bond angles, okay? So here we go. I'm going to erase this so I can do some more writing here with these expanded structures. Okay, the first one we're looking at here is a trigonal bipyramidal. Now, all of these structures, the trigonal bipyramidal, seesaw, T-shaped, and linear here, are all going to have 5 electron domains. Okay, all of them, 5 electron domains. That includes bonding pairs and lone pairs of electrons. Okay, so with 5 bonding pairs, or 5 bonding domains, or 5 domains in general, this means that we're definitely going to have an extended or expanded valence shell octet. Okay, so for an example for trigonal pyramidal, first of all, let's look at the angles. Okay, there's going to be 2 angles here. You're going to have a 90-degree angle here, and between these ones here is going to be 120-degree angles. Okay, that didn't write out very well. 120-degree. All right. So with trigonal bipyramidal, you have 2 angles, 90 and 120, to learn. A good example, I think, is P, CL, 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 CL. Okay, so this would be basically PCl5. All right. Now, if you look and count or the make that a little bit better of a bond there. Alright, so if you count the number of electron domains, you would have 5. And so this right here is going to be 90 degrees. 90 degree angles. And then these angles here are going to be 120 for the trigonal bipyramidal. Alright? Alright, now, seesaw. Reset so I have a little bit more room. Okay, seesaw now. Seesaw, 5 electron domains, but one of them is a lone pair. So that lone pair is going to need more space. So you still have a 90 degree angle there, but this angle here is going to get smaller because of that lone pair. And that's going to now be a 117 degree angle. Okay? A good example of a seesaw is let's see, sulfur molecule. Sulfur is, by the way, phosphorus and sulfur are both common atoms that have extended octets, right? And so that's why I'm going to use sulfur and phosphorus a lot when we do extended octets, right? They just have a good ability to do that. And so therefore we have 90 degree angle here and a 117 degree angle there. So we just have SF3. And SF3 has that lone pair of electrons, which then creates that smaller 117 angle instead of 120. Okay, so there's seesaw for you. Alright, the next, oh, by the way, the seesaw, if you look closely, it does remind you a little bit of a seesaw. Here's kind of where someone would be like sitting. Someone would be like sitting on this side, and someone would be sitting on this side, and these are the legs, and so it's going to be teetering back and forth like a teeter-totter or seesaw, back and forth, up and down. So that's where it kind of gets the seesaw shape from. Alright, so let's go to the T-shape. The T-shape is easy because it looks like literally a T. Okay, you literally have a T, therefore it's T-shaped. Alright, now T-shaped, you have the 2 lone pairs now, and so the bond angles for the T-shaped are going to be solely 90 degrees, all of them. Alright, so a good example of a T-shaped, let's do chlorine. Chlorine is a big enough atom. It also can have an extended octet. So 1, 2, 3, and then it's going to have its lone pairs here, like so. Alright, and so there's your 90 degree angle with that. So ClF3 is our idea there. Okay, so just the T-shape. Alright, finally we have a linear shape, and linear again would denote that the bond angle must be 180 degrees. It must have a 180 degree bond angle due to those 3 lone pairs, because those 2 bonding domains, the furthest they can really get away from is 180 degrees. Okay, what's an example? Well, this is where we're going to finally look at noble gases. Okay, now you know very well, I think, that understand that noble gases have full valence shells, and so noble gases typically do not form bonds whatsoever. But there are some exceptions to that when we look at expanded valence shell theories. Alright, xenon, being a noble gas, being kind of a fairly big sizable atom, we have the ability to force xenon to make some bonds here. Very rare, you don't really find this again in nature, but we can do it in a laboratory setting. Okay, so we have the lone pairs here. right? And that's going to make better dots. Okay, lone pairs around the Xeon. That gives us an extended octet. Notice it has 2, 4, 6, 8, 10. Man, I can do better drawing. Okay, here's a better drawing. Xeon, and then you have fluorine, and another fluorine, and the lone pairs. There we go. Now you can see now it has 2, 4, 6, 8, 10. 10 electrons around the central atom, having that extended octet. Okay? And again, the bond angle here would be 180 degrees. Right? So that would be all the shapes that are extended with 5 domains, electron domains essentially. Okay? Alright, finally, these are the last 3 that we're going to discuss. Yay! Alright, these all have expanded octets or expanded valence shells as well. They have 6 electron domains, each one of these. Alright? However, the good news is that even though you have to worry about learning the names of the shapes, the good news is they all have the same angles. All octahedrals, square pyramidals, and square planars all have 90-degree bond angles. So that's going to make that simple for us. So, let's focus on our octahedral first. The octahedral has 6 bonding domains. They're all bonding, no lone pairs. Let's go to sulfur again. Remember I said sulfur is a great one to have an extended octet. So let's do sulfur hexafluoride. This would be just SF6. Okay, so 6 fluorines around it. And notice that the number of bonding domains is 1, 2, 3, 4, 5, and 6. And therefore it has 2, 4, 6, 8, 10, 12 valence electrons in that expanded octet. Okay, so well violating the octet rule. Okay, that's okay. Sulfur has the ability to do that. So again, our sulfur, fluorines, and the bond angles, 90 degrees, all the way around 90 degrees, okay? So there's an octahedral for us, all right? Let's go to a square planar, again, or a square pyramidal. Again, the square pyramidal has 6 electron domains, but one of them is a lone pair, all right? But still, it allows us to have a 90-degree angle with that square pyramidal. Let's do an example. Let's do bromine again. Bromine is pretty good at, you'd have to make that smaller. Bromine and fluorine. Notice I use fluorine a lot. Fluorine's pretty typical used in these expanded. Right, and then we have a lone pair. So this would be BRF5 would be the formula for this. And again, the bond angles are 90 degrees for the square pyramidal. Right? And our last one finally is the square planar. Alright, yay, we finally got to the last one. I know this is a lot, but you guys can do it. Alright, square planar. Again, the good news, they have 90-degree bond angles all the way around. Example, let's do xenon again, our noble gas. It's going to bond with fluorine. So we have a formula of xenon F4. And that's going to put 2 lone pairs on xenon, like so. Alright. So, again, 90-degree bond angles. even with those two lone pairs. Okay, good. So these are all the shapes that you're required to know and learn in the bond angles, so make sure you spend some good time studying those ideas. Okay, one last thing I want to talk about, and that is, what if you have a more complex structure with multiple geometric centers, okay, or multiple centers? Like in this case, you have a carbon that's a center there, you have a carbon center there, and you have an oxygen that is also a central. And you can see it's a central because there's a hydrogen and a carbon attached there, they're making that a central atom, okay. But you also know that this is central because this oxygen, and that carbon is surrounding it, making it a central atom. And then, of course, this last central atom has those hydrogens and that carbon surrounding it. So we have three geometric centers. Because we had three geometric centers, we have three shapes. So you have to look at each one individually to decide what the shape would be. Okay? So let's look at this first carbon. Let's count how many electron domains around this carbon. We have 1, 2, 3, 4. There are 4 domains around that central atom. They're all bonding pairs. So what's the shape around this central? It's going to be a tetrahedral. Okay? This is a tetrahedral structure. Alright? So we got that one identified. So what about this other carbon in its central? How many bonding domains? You have 1, 2, 3. That has 3 bonding domains. Now go back and look at your notes. What is the geometric shape for a molecule with 3 bonding electron domains? You should find that it is a trigonal planar. Alright, and those angles are 120 degrees. All the way around, these are 120 degree angles. These, by the way, are 109.5 because they're tetrahedral. Alright, so we have a tetrahedral structure and a trigonal planar around those 2 carbons. Now, what about the oxygen? How many around there? Well, what's not shown here is that it has lone pairs. Okay, 2 lone pairs. Alright, so how many domains does this oxygen have? It has the 2 lone pairs plus these 2 bonding pairs. That's 4 domains, but 2 of them are lone pairs. Well, that looks like a bent structure of 105 degree angles. Alright, so if you look at your notes. So it tells us then we have a you have a tetrahedral around that carbon, a trigonal planar around that carbon, and this oxygen has a bent structure around that geometric center. Alright, and so that's how you would do it. Alright, I know this is a long lecture video. There's a lot of important things here to know. So make sure you study your notes really super well. Learn these shapes, learn the bond angles. A lot of students resist learning this, and that is a big mistake. These shapes are really important for your test, okay? So learn them, and that is it for now.